Welcome to Deep Thinkers. Let yourself get comfortable now. Wherever you are, however you're lying, let your shoulders drop just a little further into the softness beneath you. There is nothing you need to do for the next while. Nothing to solve, nothing to hold on to. You can let your eyes rest closed and let the sound of these words be the only thing you follow. The way you might follow a slow river with your gaze, not swimming in it, just watching it move. Tonight we are going to travel very far away from this room, farther than any place, into a time so distant that the very ground beneath the continents had not yet settled into the shapes we know. And we are going to visit a version of our own planet that you would not recognize. A white world, a frozen world, an Earth swallowed whole by ice. Let me begin with a number, and let it settle over you gently, the way snow settles. 57 million years. That is how long the longest winter in the history of this planet is thought to have lasted. Not 57 years, not 57,000, 57 million years of unbroken cold. A single ice age so vast in time that if you tried to walk through it, generation after generation, you would never reach the other side. This was the Sturtian glaciation, and it began around 717 million years ago, and it did not release its grip until roughly 660 million years ago. To give that a shape you can hold, imagine the whole span of time since the last dinosaurs walked the Earth, that famous 66 million years that feels almost unimaginably deep. The Sturtian winter lasted nearly that long, all by itself, all in one continuous freeze. It is the longest single ice age we have ever found written in the rocks. And for the entire length of it, the world lay quiet under a lid of ice. Now here is the strange part, the part that makes the scientists who study this pause and shake their heads even now, after decades of looking. The ice did not stay politely at the poles, the way ice does today. It did not gather into two white caps at the top and bottom of the globe and leave the warm middle alone. No, the ice came down. It crept and crawled and spread from the poles toward the middle of the world, across the temperate zones, past where the great forests would one day grow. And it kept going, down into the tropics, down to the equator itself. Glaciers, rivers of moving ice, stood at the equator. Ice reached the sea, reached sea level, in the very latitudes where today you would find palm trees leaning over warm turquoise water, where the sun sits nearly straight overhead at noon and the air hangs heavy and hot. There, in that band of the world we think of as the last place ice could ever survive, the glaciers stood at the shoreline and carved their frozen fragments into a freezing sea. We know this. This is not a guess pulled out of the air. It is written into the stone, and I want to tell you where, because the place is real, and you can hold it in your mind like a small warm stone in your palm, even as we talk about cold. In the south of Australia, there is a range of ancient weathered hills called the Flinders Ranges, low and red and folded. Some of the oldest exposed landscape you will find anywhere. And within those hills lies a body of rock called the Elatina Formation. The Elatina Formation is made of the debris that glaciers leave behind, the chaotic, jumbled rubble of a moving ice sheet. And when scientists measured the ancient magnetism locked inside those rocks, a kind of fossil compass frozen into the minerals at the moment they were laid down, the reading told them something almost impossible to believe. At the time those glacial sediments formed, that patch of ground sat within about 10 degrees of the equator. 10 degrees, practically on the tropical line. Glaciers at the tropics, at sea level. That single measurement more than almost anything else, is why we believe the whole planet froze. Because if there was ice even there, in the warmest belt of the world, then there is very little room left anywhere for warmth to hide. So this is the world we are visiting tonight. A planet gone white from pole to pole. Seen from space, if any eye had been there to see it, it would have looked less like the blue marble we know, and more like a smooth, pale pearl. A single soft globe of ice and snow turning slowly against the black, catching the light of a dimmer, younger sun. And the scientists gave this frozen world a name, one that fits it perfectly and that I find beautiful. They call the whole span of time the Cryogenian Period. Cryogenian, the word comes from Old Greek roots that mean, quite simply, the birth of ice. The birth of ice, as if the ice itself were something being born, something that came into the world and lived and grew and then, eventually, passed away. And that, in a strange way, is exactly what happened. The ice was born, and the ice lived for an unimaginably long time, and then the ice died, and out of its ending came something entirely new. But we are getting ahead of ourselves. Let the birth of ice sit with you for now. The Cryogenian, a period of the Earth's deep history named not for a place or a person, but for the ice itself. And within the Cryogenian, there was not one great freeze, but two. First, the Sturtian, that 57-million-year monster we have already met. And then, after a long pause we will come to, a second freeze called the Marinoan, younger and shorter but no less severe, which ran roughly from 650 million years ago until about 635 million years ago, when it ended, sharply, almost suddenly, in geologic terms. Two freezes, 2 times the whole world went white, and that too is a mystery we will hold on to. Because a planet that freezes solid should, by every intuition we have, stay frozen. The wonder is not only that it happened once, the wonder is that it happened, and then thawed, and then happened all over again. 2 births of ice. 2 deaths. Now, before we go any deeper, I want to be honest with you about something. Because this is a story with a genuine mystery still living inside it, and I would rather sit with you in that honest not knowing than pretend the whole thing is neatly solved. Scientists agree that the world grew catastrophically cold. They agree that ice reached the tropics. But there is a real and unresolved debate, a quiet argument that has run for years and has not fully ended, about just how complete the freeze truly was. On one side stand those who picture a hard snowball, a planet frozen surface to shore, every ocean sealed beneath ice from the poles all the way across the equator, not a single open patch of water anywhere on the whole blue face of the world. A total freeze, a planet turned entirely to stone and ice. And on the other side stand those who picture something a little softer, a state they sometimes call the Slushball, or by a stranger and more poetic name, the Jormungand state, after the great serpent of old northern myth that was said to encircle the world. In this softer picture, the freeze was nearly total, but not quite. Somewhere around the equator, they suggest, a thin band of open water or thin, broken ice may have survived, a narrow ribbon of dark sea holding out against the white, a sliver of the ocean that never fully closed its eye. Both sides have real evidence. Both sides are made up of careful, serious people reading the same rocks and coming to different conclusions. And I am not going to resolve it for you tonight, because it is not resolved. This is the quiet mystery that will drift with us through the whole story, all the way to the end, like a question you carry into sleep and let go unanswered. Was there ever a sliver of open sea? Hold that question loosely. We will return to it, but we will not force it shut. So, let us go back to the beginning of the cold and ask the first and most natural question. How does a whole planet freeze in the first place? What went wrong, or perhaps we should say, what came together to tip a living world into a coffin of ice? The first ingredient was the sun itself, and this may surprise you. The sun that shone down on the Cryogenian Earth was not the sun we know. It was dimmer, younger, and dimmer. Our sun, like all stars of its kind, has been very slowly brightening over the billions of years of its life, and back then, 700 million years ago, it gave off roughly 6% less energy than it does today. 6% may not sound like a great deal, but across a whole planet, across the whole delicate balance of heat coming in and heat radiating back out into space, 6% is enormous. It meant the Earth began this chapter of its life already sitting closer to the edge of cold, already receiving a little less warmth from above than it would in any later age. Scientists call this the faint young sun, and it is one of the deep puzzles of the early Earth, because with a sun that weak, you might expect the whole planet to have been frozen far more often than it was. Something kept it warm through most of its history. But during the Cryogenian, that something faltered. And with the young sun already dim, the world had less warmth to spare and further to fall. That was the stage, a world lit by a fainter sun, already leaning toward the cold. Now the pieces on that stage had to move. And they did move, though slowly, over tens of millions of years in the way that continents move, which is to say about as fast as your fingernails grow, drifting across the face of the planet on the slow currents of the rock beneath. Because in the age just before the Great Freeze, the land of the Earth was not scattered into the familiar continents we know. It was gathered together, most of it, into a single enormous supercontinent, a vast assembled landmass that geologists call Rodinia. Picture nearly all the dry land of the world pushed and welded into one great body, one immense shore surrounding one immense ocean. Rodinia had stood for a long time. But around 750 to 800 million years ago, it began to come apart. The great supercontinent started to break, to rift and split along enormous fractures, tearing itself into fragments that would drift away from one another over the ages to come. And here is the crucial thing about how Rodinia broke, the detail that matters for our story of ice. When the supercontinent split apart, its pieces did not scatter toward the poles. Most of the land ended up clustered in the low latitudes, in the warm, wet belt of the world, in and around the tropics. Land gathered near the equator. And that, it turns out, is a recipe for cooling the whole planet, though it takes some patience to see why. Let me walk you through it slowly, because this is the engine that began to pull the world down toward the freeze, and it is a beautiful and quiet mechanism, the kind of thing that works without anyone noticing, over spans of time so long that no living creature could have felt it happening. It has to do with rock and rain and the slow breathing of the planet's air. There is a gas in the atmosphere, carbon dioxide, which you may know as the gas that traps heat, the blanket gas, the one that keeps a planet warm by holding on to the sun's warmth and slowing its escape into space. Without any of it, a world tends toward cold. With a great deal of it, a world tends toward warmth. And the amount of carbon dioxide in the air is not fixed. It rises and falls over the ages, controlled by a slow balance between what puts it into the sky and what takes it back out. Volcanoes put it in, breathing it up from deep inside the earth over millions of years. And rock, believe it or not, takes it out. This is the part I want you to sit with, because it is genuinely strange and lovely once you see it. When rain falls on certain kinds of rock, the common rock of the continents, the grey and speckled stone called silicate rock, a slow chemical reaction begins. The rainwater, which has a little carbon dioxide dissolved in it from the air, meets the fresh rock, and the two react. The rock slowly dissolves, weathers, crumbles at the chemical level, and in doing so it pulls the carbon dioxide out of the water and locks it up, carrying it eventually down the rivers to the sea, where it is buried away. Think of it as the rock quietly drinking the gas out of the sky. Every raindrop that touches fresh stone takes a tiny sip of carbon dioxide out of the air and stows it away in the rock. This is called silicate weathering, and it is one of the great slow regulators of the planet's temperature, a thermostat that runs on rain and stone across millions of years. Now put the pieces together. Rodinia has just broken apart, and its fragments sit in the warm, wet tropics, right in the belt of the world, where the rain falls hardest and the air is warmest. Warm, wet rock weathers fast. Rain lashes down on all that freshly exposed stone, along all those new coastlines and rift valleys, and the weathering runs quick and eager. And the rock drinks and drinks and drinks the carbon dioxide out of the sky, faster than the volcanoes can replace it. And so, across the long, slow ages, the blanket of carbon dioxide over the earth grows thinner. The gas that held the warmth in is drawn down out of the air into the stone. And a planet that is already lit by a faint young sun, already leaning toward the cold, begins to lose the very blanket that kept it warm. Can you feel where this is going? Slowly, quietly, over tens of millions of years, with no drama at all, the world was cooling. Not because of any single catastrophe, because of rain falling on rock in the tropics, day after day, age after age, drinking the warmth out of the sky, one raindrop at a time. The continents had drifted into exactly the wrong place, into the warm, wet belt where they could most efficiently strip the greenhouse from the air, and the young sun did not have the strength to make up the difference. And so the temperature drifted down and down, edging the whole planet toward a line, a threshold, a point of no return that no one on that empty world could have seen coming. We will come to that line in time. We will come to what waited just past it, the terrible feedback that could take a merely cooling world and, once a certain edge was crossed, tip it in a matter of centuries into a total planet-wide freeze. But for now, stay here, in the long, slow cooling, before the tipping. Because I think there is something strangely peaceful in it, and it is the kind of thing worth carrying towards sleep. A whole planet growing colder, not through any violence, but through the patient action of rain on stone. The rock drinking the sky. The land in the warm places, quietly weathering, quietly pulling the warmth down out of the air, over spans of time so vast that 1,000,000 years is only a moment. Let me hold this image with you a little longer, because we have all the time in the world tonight and no reason to hurry. Imagine standing on the shore of that ancient tropical sea, before the ice, in the long twilight of the cooling world. The continents of Rodinia are still pulling apart somewhere over the horizon, so slowly you could never see it move. The sun overhead is a little paler than the one you know, hanging in a sky that has no birds in it, because birds will not exist for hundreds of millions of years. No birds, no trees, no grass, no green thing at all upon the land, only bare rock and water and sky. The rain comes, as it always comes in the tropics, warm and heavy, and it runs down the naked stone in sheets. And where it touches the fresh grey rock, it begins its slow, quiet work, dissolving the stone grain by grain, drinking the carbon dioxide, carrying it away to the sea. There is no sound but water and wind. No creature stirs on the land. And year by year, century by century, in a silence deeper than any silence you have ever known, the world grows colder. And the strange, tender truth of it is that this cooling, this long white death that was gathering, this ice that would one day swallow the entire planet, was in some sense the world simply doing what worlds do, balancing, breathing, the rock and the rain, and the drifting continents settling toward a new equilibrium the way water settles when you stop stirring it. There was no malice in it. There was no catastrophe. Not yet. Only the slow arithmetic of a planet, the young sun and the tropical land and the weathering stone, all leaning together in the same direction, all pulling the temperature gently downward toward the edge of something none of them could have understood. And this brings us to the heart of the paradox that will guide us through this whole long night. So let me lay it before you now, softly, and then let you rest with it. Here is a world cooling itself toward total ice. And once that ice fully takes hold, once the whole planet is wrapped in white, it will become a trap, a frozen prison so complete that by every ordinary rule it should never be able to thaw. A frozen planet reflects away the sunlight that might warm it. A frozen planet has no liquid water, and with no liquid water the rain cannot fall, and the weathering stops, and the whole delicate thermostat we just watched at work simply switches off. Everything that made the world coolable makes the frozen world, once frozen, seemingly impossible to unfreeze. The door closes behind it. The trap shuts. And yet we know the world thawed. We know it, because we are here, because there is warmth around you now, and open water on the earth, and the sound of my voice, and the softness beneath you. The ice did not win. Twice the world froze, and twice it broke free. So the great question, the one the whole story bends toward, is this. What force could possibly melt an entire frozen planet? A planet that had shut off its own thermostat and sealed itself in white and thrown away the key. What quiet, patient thing was building all through the millions of years of the freeze that could one day break the ice and give the world back to the light? There is an answer. It is one of the most beautiful and unlikely answers in all of Earth's history. And it involves the very same gas we have been watching disappear, the carbon dioxide that the rock drank out of the sky. Because when the world froze and the rain stopped and the weathering shut down, the drinking stopped too. And there was still one thing that never stopped. One deep, slow process that no amount of ice could silence. But that is the centerpiece, and we will build to it carefully, the way you build toward the deepest part of sleep, in no hurry at all. For now, let the paradox hold you. A world cooling itself into a trap it should never escape. The rock drinking the sky in the warm tropics. The faint young sun. The great supercontinent breaking apart into the wet places of the world. The temperature drifting down and down toward an invisible line. And beyond that line, waiting, the ice that would swallow the entire planet and stand at the equator and hold the world in silence for 57 million years. Breathe slowly now. There is nothing to fear in this cold. It happened so long ago that all its terror has softened into wonder. The way a storm seen from very far away becomes only a beautiful darkening of the sky. We are watching a planet fall asleep under a blanket of ice. And in a strange way, we are learning that even a world can rest, can go quiet and white and still for an unimaginably long time, and then wake again, changed into something new. Let me return, gently, to that measurement in the Australian hills, because I want it to be the image you hold as we drift toward the next part of the story. The Elatina Formation, in the folded red rock of the Flinders Ranges, a body of stone that is nothing but the leavings of a glacier, the crushed and jumbled rubble that ice carries and drops. And locked inside it, that fossil compass, that faint magnetic memory pointing back to the moment the rock was made, telling us that this glacial debris was laid down within 10 degrees of the equator. When I first understood what that meant, I remember the feeling of it, the small vertigo of it. It means that if you had stood on the equator of the Cryogenian Earth, in the place that should be the hottest ground on the whole planet, you would have looked up and seen a glacier, a wall of ice, moving, grinding, in the tropics, ice at the waterline where the warmest sea should lie. The whole intuition of the world turned inside out, the tropics frozen, the equator white. That is the world we have come to visit, and we have only just arrived at its shore. Now let the cold settle around you, not as a threat, but as a kind of vast and ancient quiet. The continents drifting into the warm belt of the world, the rain falling on the naked stone, the rock drinking the carbon dioxide, sip by patient sip, out of a sky lit by a fainter sun. The temperature sliding downward across tens of millions of years toward a line no one could see. And on the far side of that line, the birth of ice. The Cryogenian, the longest winter Earth has ever known, gathering itself quietly in the deep silence of a world with no witnesses at all. We have the whole night ahead of us to watch it happen, and then to watch it break. So there is no need to hold on to anything now. Let the slow cooling of that ancient Earth match the slow cooling of your own thoughts as they settle. Let the raindrops falling on that empty tropical shore be the last small sounds you follow down into rest. The world is growing colder and quieter and stiller, and there is nowhere you need to be and nothing you need to carry, and the ice is coming. Slowly. From the poles toward the middle of the world, and it is going to take its time, and so can you. Stay with me. There is so much more to see, and we are only at the very edge of the ice. Let me tell you where the name came from, because it is a gentle thing to know as you drift. Cryogenian, the word means, quite literally, the birth of ice, not the cold that comes and goes with a season. Not the frost that melts by noon. The birth of ice as a force that shaped an entire planet, that wrote itself into stone we can still read today. Someone, long after, standing in a quiet room, looked at the evidence of that frozen world and gave it a name that sounds like a lullaby for a planet. The birth of ice. Say it slowly to yourself, and it almost rocks you. And here is the strangeness at the heart of it, the thing that should not make sense. Ice belongs at the poles. That is what every part of you already knows. The white caps sit at the top and the bottom of the world, and the middle stays warm, and that is simply how a planet is supposed to be arranged. But the stones of the Cryogenian tell a different story, and they do not stutter when they tell it. In South Australia, in a place called the Flinders Ranges, there is a body of rock called the Elatina Formation. And when scientists read the magnetism locked inside those ancient sediments, the tiny compass needles of iron that froze into place as the rock formed, the answer came back that made no ordinary sense. This rock, this glacial rubble dropped by moving ice, was laid down within 10 degrees of the equator. 10 degrees. Right in the warm belt of the world. Glaciers standing where the tropics are now. Ice grinding down to the level of the sea in the one place on Earth that should never freeze. That is the paradox we will carry with us all night. If the equator froze, then there was nowhere warm left. Nowhere at all. And if there was nowhere warm left, how did anything survive to see the other side? And stranger still, if the whole planet locked itself in white, if the ice covered even the middle of the world, then what force in all of nature could ever be strong enough to melt it again? A frozen planet reflects the sunlight away. A frozen planet stays frozen. It is a trap that closes behind you. And yet here we are, alive, warm, breathing, on the far side of that trap. So something opened it. Something let the world back out. We will get there, slowly, in the deep hours ahead. But hold on to one small thread of mystery as we go, because the scientists themselves still hold it. When they say the whole planet froze, they do not all mean quite the same thing. Some picture a hard shell, ice from shore to shore, every last wave stilled, the ocean sealed under a lid from pole to pole to pole. Others picture something softer, a slushball, a world almost entirely white, but with a thin ribbon of open or slushy water somewhere near the middle, a place where the sea still breathed against the sky. Both sides read the same stones. Both sides are careful, serious people. And the question of whether there was ever a sliver of open sea has never been fully settled. It is the quiet mystery running under everything, and I am not going to pretend it away for you. We will let it stay open, the way the real question stays open, all the way to the end. For now, though, let us go back to the beginning of the cold, before there was any ice at all, and watch how a warm world talks itself into freezing. Start with the sun. The sun that hung over that ancient Earth was not the sun you know. It was fainter, dimmer by about 6%, a younger star that had not yet grown into its full brightness. 6% does not sound like much when you say it softly like this, but 6% less warmth pouring down, day after day, age after age, means a world that starts from a colder place. A world already leaning toward the cold, already closer to the edge than ours, waiting for something to give it the smallest push. And then the land itself moved to help the cold along. In that deep time there was a single great gathering of continents, a supercontinent called Rodinia, and around 750 to 800 million years ago it began to come apart. The land broke and it drifted of all the directions it could have gone into the warm, wet belt of the tropics. Picture bare rock, no grass, no forest, no soil to speak of, just naked stone, sitting now in the rainiest, warmest part of the world. And the rain fell on it, endlessly, softly, year after year after uncountable year. Rain on bare rock is not a gentle nothing, it is a slow chemistry. When rainwater touches certain kinds of stone, the silicate rock that makes up so much of the land, it pulls carbon dioxide out of the air and locks it away, sip by patient sip, into dissolved minerals that wash down to the sea. Carbon dioxide is the blanket that keeps a planet warm. And here was the whole warm, wet tropics, covered in fresh, naked rock, drinking that blanket down out of the sky. Thinning it, loosening it, letting the warmth leak away into space a little faster with every passing age. Slower and slower the world grew warm. Cooler and cooler it slid, toward a line it could not see, and could not feel, and could not stop itself from crossing. And then the fuse was lit. Somewhere beneath what is now the northern edge of North America, deep in the mantle where rock is not solid so much as it is slow and vast and endlessly churning, a column of unusual heat had been building for a very long time. The kind of heat that does not announce itself. The kind that gathers quietly, pressing upward through kilometers of stone, finding the thinnest places in the crust and pushing there, patient and enormous, until the rock above can no longer hold. Around 717 million years ago, it gave way. And what came through was not a single eruption, not a mountain blowing its crown. What came through was a flood. Geologists call it the Franklin Large Igneous Province. The name is plain and technical, and it does almost nothing to suggest the scale of what it describes. A large igneous province is what happens when the planet hemorrhages. When the mantle punches through the surface, not at a single point but across a vast region, and lava simply pours out and out and out over thousands of kilometers, over hundreds of thousands of years, until the landscape is buried under layer upon layer of fresh black basalt. The Franklin event draped enormous sheets of that dark rock across what is now northern Canada. Where before there was varied terrain, there was now a dark basalt-covered plain stretching toward every horizon. In ordinary circumstances, new basalt is just new rock. But these were not ordinary circumstances. Remember where the continents had drifted. The land was sitting low in the warm and rainy tropics, and fresh basalt, geologically speaking, is among the most reactive of rocks. It is full of minerals that have never been touched by air or water, minerals that are chemically hungry, that react fast when rain finds them. Put a sheet of fresh basalt in the wet tropics, and you have essentially laid out an enormous welcome mat for the rain's slow chemistry. Every drop of water that fell on that new dark stone pulled a little more carbon dioxide out of the sky. Not dramatically, not violently, just steadily, relentlessly, across hundreds of thousands of years, faster than before, more thoroughly than before. Because the rock was fresh, and the climate was warm and wet, and the weathering ran hard. The blanket thinned a little more, the warmth leaked a little faster. The planet cooled a fraction of a degree here, a fraction of a degree there, across geologic time that is so vast it would take you 1,000 lifetimes just to count in years, let alone to feel it in your body. But the cumulative effect was real, and it was directional, and it was moving the world towards something. It was moving it towards snow. At first, that seems like it should be fine. Planets have ice ages. They always have, they always will. Ice comes and ice retreats, and the world keeps turning. Snow falls in the high latitudes, builds up into glaciers. The glaciers slide to the sea. And life carries on in the warm middle of the world between them. This is normal. This has happened many times. But there is a version of this that is not normal. There is a version where the ice does not stop at the high latitudes. There is a version where it keeps coming. And that version has a physics to it that is deeply, almost beautifully merciless once you understand it. Ice is white. This is not a trivial thing. White reflects light. When sunlight hits snow or ice, most of it bounces straight back into space rather than being absorbed and turned into heat. The technical word for this reflectivity is albedo, and fresh snow has an extraordinarily high one, returning up to 90% of the sunlight that falls on it without warming the surface at all. Compare that to the dark ocean, which absorbs nearly all the sunlight that reaches it, soaking the heat in, warming the water, warming the air above. The difference between a white surface and a dark one, in terms of how much energy the planet captures from the sun, is enormous. Now imagine the ice advancing. As the world cooled, glaciers grew in the polar regions, as they always do when the temperature falls. And as the glaciers grew, the surface that had been dark ocean or dark rock became white. And that white surface reflected more sunlight, which cooled the planet a little more, which grew the ice a little further, which reflected a little more sunlight, which cooled the planet a little more. You can see where this goes. It is a loop. It feeds itself. Every step makes the next step easier, and the step after that, and the step after that. Climatologists call it the ice albedo feedback, and it is one of the most powerful, self-reinforcing cycles in Earth's climate system. Once it starts in earnest, it is very hard to stop. For a long time, the planet has a stabilizing force working against this loop. Carbon dioxide in the atmosphere keeps enough warmth in that the feedback cannot run away completely. The ice stays in its place, held back by the warmth of the tropics, unable to push past a certain latitude. The world finds a balance and holds there, cold and settled, but not catastrophically so. But if something has been draining the carbon dioxide out of the sky, as something very clearly had been during these long, slow ages of Rhodinia's breakup and the Franklin basalt's weathering, then the stabilizing force weakens. The atmospheric blanket gets thinner and thinner, and as it thins, the tipping point moves. The latitude at which the feedback becomes unstoppable moves closer and closer to the equator. Two scientists named Mikhail Budyko and William Sellers worked this out independently of each other in 1969. They were building mathematical models of Earth's climate, trying to understand how the global energy balance worked. What happened if you changed the amount of sunlight arriving or the amount being reflected away? And what they found, when they ran their numbers, was something that surprised them. There was a threshold, a line you did not want to cross. If the ice advanced far enough south, past roughly 30 degrees latitude, the feedback became self-sustaining. The reflectivity of the ice was enough, at that point, to overwhelm whatever warming the remaining greenhouse gas could provide. The planet could not hold itself back. The whole thing ran away. Centuries, that is the timescale once you cross 30 degrees. Not millions of years. Not thousands. Centuries, the difference between a planet with temperate zones and a planet wrapped in ice from pole to equator, is a few hundred years of planetary time. From a geological perspective, that is essentially instantaneous. A blink. You turn the page of a chapter and the whole world has changed. The ice came. Not in a rush that any creature could perceive, because 700 million years ago, the creatures that existed were tiny and simple single cells or loose colonies of cells with no eyes to watch and no minds to register alarm. But in the time those creatures lived and died and lived and died, generation after uncountable generation, the white edge crept southward. The equatorial ocean, which had been warm and lit and full of the soft chemistry of life, began to cool. The ice touched the surface at first only in the shallow coastal waters near the polar shores, and then it spread, and the surface temperature fell, and more water froze, and more sunlight was reflected, and the temperature fell again. And the feedback held nothing back now, because there was not enough carbon dioxide left in the sky to hold it back, and Rhodinia's wet tropics had seen to that, and the Franklin basalt had seen to that, and the faint young sun had seen to that. all of them together, pushing and pulling the world toward this moment, this crossing. And then the crossing happened, and then it was over. The equatorial ocean froze. Let that sit for a moment, because it is a fact that resists being fully imagined. The equator is the warmest place on Earth. It always has been. The equator is where sunlight strikes the planet most directly, where it lands nearly perpendicular to the surface and delivers its maximum possible energy. Every ocean current, every wind pattern, every ecological distribution on the planet is organized around the fact that the tropics are warm. And yet the rock record says, plainly and without ambiguity, that the ocean froze there. Not just chilled, froze, solid ice, where the warmest water on the planet should have been. The evidence we have from South Australia tells us this with remarkable clarity. In the Flinders Ranges, a long series of ancient hills rising from the South Australian plains, there is a layer of rock called the Elatina Formation. The Elatina Formation is made up of diamictite, a particular kind of sedimentary rock that only forms in one way. Diamictite is chaos in stone. It is a jumbled, unsorted, chaotic mixture of all kinds of material, everything from fine clay particles to boulders as big as a house, all crammed together without any of the sorting that water does naturally. When a river carries sediment, it sorts it, the heavy stones dropping first, the lighter sand and silt travelling further, the clay drifting furthest of all. Running water is a sorter, but ice is not. A glacier picks up everything it can reach, grinds it together, carries it in a tumbling, unsorted mass, and dumps it when it melts. The resulting rock, when you find it millions of years later, looks like frozen disorder. Chaotically mixed, unsorted, the signature of ice. And the Elatina Formation's diamictite was deposited at a paleolatitude within 10 degrees of the equator. Geologists know this because of a property of certain minerals in rock. When rock forms, iron-bearing minerals align themselves with Earth's magnetic field, like tiny compasses frozen in place as the stone solidifies. And the angle at which they align tells you how close to the equator you were when the rock formed, because Earth's magnetic field lines run steep near the poles and flat near the equator, and the minerals record that angle, and the angle cannot easily be changed by later geologic processes. When you measure the paleomagnetism of the Elatina Formation, you are reading a message from the minerals themselves, and the message says, this rock formed within 10 degrees of where the equator was at that time. This rock formed in the tropics. These glaciers stood in the tropics. The ice reached sea level in the tropics. The Elatina Formation is not alone. Diamictites from the Cryogenian Period have been found on nearly every ancient continent. When paleomagnetic data has been gathered from them, multiple deposits from multiple places on the planet record low latitudes, tropical positions at the time of deposition. This is not a local story. This is not a regional climate fluctuation, the kind where one part of the world gets cold while another stays warm. The signal is global. The pattern is the same everywhere the rock record has been read. This is a planet that froze. And what it froze into was something very different from anything the Earth had been before or has been since. The models that scientists use to understand the deep freeze give numbers that are difficult to hold in the mind. The global mean temperature during the height of the Sturtian glaciation was something in the neighborhood of -50 degrees Celsius. Not at the poles, everywhere, on average, across the whole surface of the planet, 50 degrees below the freezing point of water. To put that in terms that might mean something, the interior of Antarctica today in the deep winter, in the most extreme cold of the most isolated continent on Earth, reaches temperatures in that range. And that is what the model suggests for the equator, not the poles. The equator. The sea ice in the tropical ocean was not a thin sheet of the kind that forms on a pond on a cold morning. Models suggest the tropical ocean ice was perhaps a kilometre thick, 1,000 meters of solid ice floating on the ocean, pressing down under its own weight, grinding and creaking in a world utterly still. Below the ice, the water was dark and cold and still. Cold, but not frozen solid. The geothermal heat rising from the planet's interior, from the radioactive decay of elements in the deep rock, from the residual warmth of planetary formation billions of years before, was still there, seeping upward through the ocean floor. Not enough to keep the surface liquid. Not nearly enough for that, but enough, just barely, to keep the deep abyssal ocean from freezing entirely. Miles below the ice, in the utter darkness of the deep sea, water still moved, still existed as liquid, however cold and slow and lightless. This fact matters more than it might seem at first. We will come back to it. The sky above the ice was not silent. The wind still moved, because the temperature differences between regions still drove atmospheric circulation, though in this diminished, strange, frozen world, the patterns would have been very different from what we know. But the sound of weather was still there. The hiss of driven ice, crystals across the surface, a blowing and a scouring. A world of ice moving and refreezing and sublimating slowly at the surface in the thin, cold air. No rain. Rain requires liquid water to evaporate from the surface, and there was none available from the frozen ocean. The hydrological cycle, the great global circulation of water from sea to sky to land and back, had essentially shut down. The world was locked, frozen and locked, with almost nothing moving at the surface. It is a kind of silence that goes beyond ordinary quiet, not the quiet of a still room or a still night in winter, the quiet of a world that has stopped exchanging things, stopped breathing in a sense, stopped the endless transaction between the ocean and the sky and the rock that makes a living planet what it is. All of it stilled, all of it held. We know this world existed because people looked carefully at stones. Old stones, deeply buried, now exposed by erosion or uplifted by the slow tectonics of later ages, offering their surfaces to whoever arrives with the patience to read them. The reading requires patience because the evidence is not obvious. You cannot look at a diamictite and immediately know it came from an ice age. It looks like rough, grey, chaotic rock. It looks like confusion. You have to know what confusion in stone means. You have to know about glacial transport, about the way ice mixes everything it touches, about the sorting that water does and that ice does not. And you have to know about dropstones. A dropstone is exactly what the name says, and it is one of the most quietly elegant pieces of evidence in geology. When glaciers reach the sea, pieces break off and float away as icebergs, carrying within them whatever rocks the glacier picked up during its long, slow journey from inland. As the iceberg drifts out to sea, it slowly melts and the rocks embedded in the ice drop. They fall through the water column and land on the seafloor, on whatever fine sediment has been settling there. Fine seafloor sediment accumulates in thin, horizontal layers laid down quietly, one thin sheet at a time, undisturbed, and then a rock the size of a cantaloupe or a football or a watermelon falls out of the melting ice above and hits the seafloor and bends the layers beneath it. pressing them down and deforming them in a distinctive way that is unmistakable to a trained eye. The layers above the stone continue horizontally as if nothing happened. The layers below it are dished, curved downward by the impact. And the rock itself sits there in the middle, a stranger, a piece of granite perhaps, in a bed of clay that has nothing else like it. A message from the ice above. Dropstones from the Cryogenian Period are found in rock formations around the world. They sit in their ancient beds, surrounded by the fine layers they bent when they fell, perfectly preserved in stone, waiting for someone to notice them and understand what they mean. They mean ice was floating here. They mean icebergs were carving into these ancient seas. They mean glaciers had reached the ocean at this place and at this time, and had sent their frozen pieces drifting out into the water. These stones crossed an ocean that does not exist anymore, and they sank, and they bent the mud beneath them, and then the mud became rock around them, and then hundreds of millions of years passed, and then a geologist found them and crouched down and understood. There is something extraordinarily moving about that, if you let yourself feel it. A rock that fell through ancient water and is still there, still telling its story, perfectly preserved in the record of the earth. The story took a very long time to read. Not because the evidence was hidden, but because no one knew quite what to make of it. The rocks were old, deeply old, from the Precambrian, from the time before complex life, and Precambrian geology was for a long time a relatively small field, a quiet corner of earth science. But certain people were looking. A British geologist named Brian Harland was one of them. In the 1960s, Harland was studying Precambrian rocks, collecting paleomagnetic data, trying to understand where the ancient continents had been, and he noticed the low-latitude glacial signal. He noticed that there were glacial deposits from that distant time sitting at what the paleomagnetism said were tropical and equatorial latitudes. He published on it. He argued that the evidence pointed to a near-global glaciation of the Precambrian. He was largely met with skepticism. The idea was too large, too extreme, too incompatible with the intuition that if the whole planet had ever frozen over, the evidence would somehow be more obvious, or the consequences for life more clearly catastrophic. It sat at the edge of acceptability for decades, noticed but not embraced. Then a geobiologist named Joseph Kirschvink picked it up. Kirschvink was at the California Institute of Technology, and in 1992 he contributed a short but remarkable piece to a volume called The Proterozoic Biosphere. It was not a long argument, but it was a precise one. Kirschvink took Harland's glacial evidence, took the ice albedo feedback physics, and built a coherent model. He argued not just that the planet had frozen, but that the freezing was a runaway process, that once the feedback crossed its threshold, there was no intermediate stable state, and that the planet plunged all the way to a full global glaciation. He gave it a name, Snowball Earth, and then, in the same short piece, he supplied the key that unlocked the escape. He recognized what would happen to volcanic CO2 if the surface froze. He recognized the trap and described how the trap eventually breaks. The word Snowball Earth and the essential logic of both the catastrophe and its resolution came from those pages. Kirschvink gave the idea its name, its mechanism, and its exit. But the idea needed more than a name. It needed the full weight of evidence assembled and presented clearly enough that the wider scientific community could not easily look away. That happened in 1998, in a paper published in the journal Science. The authors were Hoffman and Daniel Schrag. Hoffman was a Harvard geologist who had spent decades studying ancient rocks in Namibia, in the Flinders Ranges, in places around the world where the Cryogenian record was exposed. Schrag was a geochemist. Together they wrote what would become one of the most discussed papers in the history of Earth science, a paper simply called a Neoproterozoic Snowball Earth. It brought together the glacial deposits at low latitudes, the cap carbonates sitting directly on top of the glacial debris, the carbon isotope excursions that recorded the near collapse of ocean life, the ice albedo feedback, Kirschvink's CO2 escape mechanism, and the geochemistry of the deglaciation. They presented it not as a curiosity or a speculation, but as a fully integrated model with testable predictions. They made the case that the planet had been utterly frozen not once, but twice in the Cryogenian, and they explained how each time it had eventually escaped. The paper generated enormous conversation, some of it enthusiastic, some of it deeply skeptical. The idea was still extreme. A completely frozen Earth contradicted the intuitions of many geologists and biologists, and it raised the immediate question of how any life at all had survived. Critics pointed out that the same geologic record that showed glacial deposits at low latitudes also showed, in some cases, evidence of waves, of liquid water, of open ocean conditions at times that should have been fully frozen. They said, if the planet was completely iced over, if there was no open water anywhere, then you would not find wave ripples in those rocks. You would not find structures that indicate a working hydrological cycle. These critics proposed an alternative, not a snowball, a slushball. Perhaps, they said, the ice never fully closed. Perhaps in the tropics along the equator there was a narrow band of open water, or at least thin, slushy ice that allowed some exchange with the atmosphere, some liquid somewhere, some light penetrating to a photosynthesizing ocean. This alternative has its own name, the Jormungand state, after the great serpent of Norse mythology that encircles the world. The idea is that the planet could lock into a partially frozen state without going all the way to a complete ice cover, held there by a slightly different balance of feedbacks. The tropical open water would reflect less sunlight than ice, absorbing enough warmth to prevent the total closure, while the ice elsewhere kept global temperatures brutally cold. The honest answer, the one the evidence actually supports right now, is that this debate is not resolved. Both camps use real data. Both have legitimate geologic observations on their side. The field has not fully settled which version of events actually occurred, and in some ways the question may not have a single answer, because the two freezing episodes, the Sturtian and the Marinoan, may have differed from each other. It is entirely possible that one was a harder freeze and one was slightly more open. What is not debated is the essential reality. Something extreme happened. Ice reached the equator at sea level. The planet was colder than anything alive today has ever experienced. The word snowball describes it well enough as a shorthand for catastrophe, even if the finest details of whether every last square meter of tropical ocean surface was solid ice or slushy or open remain a subject of genuine scientific inquiry. Paul Hoffman became the most prominent advocate for the hard snowball version. He spent years after the 1998 paper gathering more evidence, defending the model, refining it, arguing with the critics. The debate that followed his paper and Schrag's is one of the livelier chapters in recent Earth science, the kind of scientific argument that has sharpened the questions even when it has not fully settled them. That is what good scientific argument does. It does not always close a question. Sometimes it sharpens it until the question is precise enough to eventually be answered. What was not seriously disputed was the depth of the freeze. The models, the rock chemistry, the global distribution of the glacial deposits all pointed in the same direction. A planet that was cold in a way that has no parallel in the human imagination. A world where the equator was like the deep interior of modern Antarctica. A world locked in its own surface, separated from its own sky by a kilometre of ice, still and dark and frozen for millions upon millions of years. And beneath all of that, something small was still alive, something the ice had not reached. Because life had been on this planet for a very long time before the Cryogenian. Billions of years by that point. And whatever had survived up to that moment had done so through the cold and the dark and the suffocating sealed ocean in ways that speak to a tenacity in living things so fundamental that it barely registers as surprising, and yet, when you hold it clearly in mind, is among the most astonishing things there is to know. The question of how anything photosynthetic survived, how anything that needed sunlight managed to keep its chemistry going in a world sealed under ice, is a question that takes you into some of the quietest and most improbable corners of this frozen world. But first, the sealed ocean, the trapped planet, and what that trap was slowly, invisibly, inexorably building toward. Because while everything above the ice was still and locked and silent, something was still happening beneath it. Something that would take millions of years to accumulate, but would eventually become large enough to shatter the very freeze that made it possible. The volcanoes did not stop. They never stop. Not really. Not on a geologically active planet. The mantle still churned, the tectonic plates still moved, and where they dove into the mantle, rock melted, and where they pulled apart, magma rose, and at the hot spots under the ocean, lava pushed through the seafloor and cooled into new stone. All of this continued, regardless of what was happening at the surface. The volcanoes beneath the ocean floor breathed their gas into the water. The volcanoes on land, those that had pushed their cones up through the ice or had erupted at the edges of the frozen ocean, breathed their gas into the air. Carbon dioxide, mostly the same carbon dioxide that Rodinia's tropical weathering had been drawing down. The same gas that had thinned as the blanket and allowed the chill to deepen was still being added to the atmosphere. A slow, steady addition. Not dramatic, not visible, just constant. In a world with liquid water at the surface, this would not have mattered so much. Liquid water means silicate weathering. Silicate weathering means CO2 gets pulled out of the sky as fast as it is added, or nearly so, and the atmospheric concentration finds a rough equilibrium, a balance point maintained by the give and take of chemistry. But the surface was frozen. The chemistry of weathering requires liquid water, and liquid water was not available at the surface anymore. The rain was not falling, the rivers were not running, the ocean was sealed under its lid of ice. Nothing was pulling the CO2 back out. And so, very slowly, millions of years of slow, the volcanic gas accumulated. This is the trap becoming its own solution, though from the inside of the trap, from the perspective of anything that might have been watching, it would have looked like no solution at all. It would have looked like nothing changing, like an endless sameness, ice and cold and sealed sky. But the chemistry of the atmosphere was changing, invisibly, continuously, driven by nothing more dramatic than the ordinary breathing of a planet that has always breathed. The CO2 climbed. It climbed through concentrations that would have been extraordinary by any standard. It climbed past what we breathe, past what plants prefer, past what the atmosphere holds today, past every reference point we have for normal. It climbed for millions of years, accumulating in the sealed cold air above the frozen ocean, with nothing to stop it, nothing to reverse it, the volcanoes breathing and breathing while the planet held still and cold and locked. And it climbed toward something, toward a number, toward the concentration at which the blanket of gas becomes thick enough, warm enough in its trapping of heat, to overcome even the extraordinary reflectivity of a planet wrapped in white ice. The point at which the math flips. The point at which more energy is being held in by the gas than is being reflected away by the ice. The point at which the planet, against all intuition, against the seeming permanence of all that frozen stillness, begins to warm. That point was coming. Slowly, over millions of years, but inexorably, because the volcanoes did not stop. Because the CO2 had nowhere else to go. Because a trap, in the end, is only a trap until the pressure inside it exceeds the strength of the walls. The ice was its own undoing. By sealing the world, by stopping the very weathering that had helped create the freeze in the first place, it had allowed the means of its own destruction to build, silently, in the air above it, for longer than most things in the history of life have existed at all. 57 million years of winter, 57 million years of volcanic breath, rising, accumulating, thickening the invisible blanket of gas above the frozen world. The Sturtian glaciation did not end because of any outside force, any passing catastrophe, any asteroid, any sudden change in the sun. It ended because of the arithmetic of a sealed planet and its own interior heat, playing out over a span of time so vast that it feels almost geological in its own right, a drama of pressure and patience rather than violence and speed. But we are still in the middle of it, still in that silence beneath the ice, still in the long, frozen middle of the Sturtian winter, which would not release the world for tens of millions of years yet. And the question that presses quietly from the dark is the one that biology raises as naturally as any other. Not just what was the ice doing to the planet, but what was it doing to the life that had been on the planet before the ice came? Whether it came as a full snowball or as something slightly less complete, it came hard and cold and total enough that the world above the ice was essentially lifeless. No trees, obviously, because there were no trees yet. No animals, because there were no animals yet. But there was life, and it had been building slowly for 3 billion years by the time the Cryogenian arrived. Single-celled organisms of various kinds, some of them the ancestors of everything complex that would ever exist. Photosynthetic bacteria that had over unimaginable time learned to take sunlight and water and CO2 and turn them into the sugars that fuel living chemistry. These organisms had transformed the atmosphere once already in the Great Oxidation Event 2 billion years before, filling the sky with oxygen as a byproduct of their metabolisms. They were the base of everything. They were the foundation. And the ice was cutting off their light. The deep ocean beneath the ice could still run on chemical energy, on the vents and the warmth from below, on chemosynthesis rather than photosynthesis. But the photosynthesizers, the ones that needed light, were facing something very close to extinction. A kilometer of ice overhead is not translucent, not in any useful sense. The sunlight that had sustained them for billions of years was being shut out by the frozen lid of the world, and something had to give, or they would simply stop. They did not simply stop. Something, somewhere, held on. We know this because the evidence is there on the other side of the freeze, because the algae persisted, because the eukaryotes persisted, because the ancestors of complex animals made it through this terrible winter and came out the other side. But how? Where? In what impossible pocket of warmth or light did they manage it? The answers to those questions are quieter than the questions themselves. They are small refugia, hidden places, the margins of a frozen world where the conditions were just barely livable. And what they reveal about the persistence of life is something worth considering slowly, in the dark, in the stillness, while the narration settles around you like the ice itself, patient and vast and full of a silence that is not quite empty. Consider the cryoconite hole. It is not a grand thing. It is not a cathedral or a canyon or a geological formation that commands the awe of whole mountains. It is a small cup, a pocket, a dimple in the surface of a glacier, and it forms in the simplest way imaginable. A speck of dark material, a grain of wind-blown dust, a fragment of mineral, a particle of carbon, something that absorbs sunlight rather than reflecting it, lands on the surface of the ice. And because it is dark, because it drinks in even the faint, glancing light that falls on it, it warms. Just a little, just enough. The ice immediately beneath it melts, a millimeter at a time, and the dark grain sinks, and the melt follows it down, and a small cylindrical well opens in the glacier's surface, wide as a thumb maybe, or a fist, or sometimes a little more, and filled at the bottom with meltwater. Liquid water, in an ice age. Real, actual liquid water, sitting inside a hole in the glacier's own body, with a window of ice above it thin enough to let light down through. The word for these holes comes from the Greek. Kryos for cold, kornitos for dust. Cold dust holes. Scientists who study glaciers today find them everywhere. On Greenland, on alpine glaciers, on the ice sheets of Antarctica. These small water-filled wells that form wherever something dark enough settles on something white enough and the sun catches it. They are ecosystems in miniature. Bacteria live in them. Algae live in them. Tiny invertebrates have been found in the modern versions, whole food chains compressed into a space the size of a coffee cup, sustained by nothing more than the thermal difference between a dark grain and the ice around it. Now hold that image and carry it back 700 million years. The Sturtian glaciation is perhaps 40 million years deep into its run. The world is frozen, the tropics are ice, the sky above is clear and cold, and the sun falls on a white planet and bounces back almost entirely into space. And the feedback that brought the freeze sustains it, this loop of cold and reflection and colder still. Somewhere in what would one day become South Australia, where the Elatina Formation is quietly being deposited, glaciers extend to sea level at a latitude that today would sit in the warm subtropics. The surface temperature at the equator is close to what you would find in the deep interior of modern Antarctica. 50 degrees below 0 Celsius, a temperature at which exposed flesh freezes in moments, at which moisture falls out of the air as fine ice crystals, at which the silence has a quality that people who have experienced Antarctic winters describe as absolute, as total, as a thing you can feel pressing against you. And yet, somewhere on the surface of the ice, a dark grain has settled, and the sun, even this diminished cryogenian sun, even the sun that is 6% fainter than the one you live under now, is still a star, and it still delivers energy to anything dark enough to absorb it. and a small well of meltwater has formed. And inside it, something is running photosynthesis. This is not a metaphor. The cryoconite holes that scientists study today are functional analogues for what may have sustained photosynthetic life through the cryogenian freeze. They are the needle's eye through which the thread of photosynthesis may have passed. They are not comfortable habitats. They are not even particularly stable ones. But life is, as it has demonstrated across nearly 4 billion years of Earth history, not primarily interested in comfort. Life is interested in just enough warmth, just enough light, just enough liquid water to let chemistry proceed at the rates that sustain it. And there were other refugia too, beyond the cryoconite holes, beyond those small dusty cups in the glacier's face. Think about what the planet looked like from within rather than from above. The surface was frozen. But the surface is not the whole of the world. Anywhere that volcanic activity came close to the surface, anywhere that magma worked its way through the crust near a coastline or an ocean basin, the rock itself would be warm. Hot springs would open in the seafloor, in the ice, along coastlines that were themselves buried under hundreds of meters of glacier. The chemistry around a hydrothermal vent does not require sunlight. It requires sulfur and heat and the dissolved minerals that volcanic water carries, and organisms had been living on exactly those ingredients since well before the Cryogenian. But the point about refugia is not just that some life survived on chemistry alone, on chemosynthesis, on the energy of the Earth's interior rather than the energy of the sun. The point is that where warm water met ice, where volcanic heat worked its way to the surface and melted through the glacier's belly, there were pockets. There were places where liquid water existed at or near the surface, where light could reach, where the conditions for photosynthesis could hold. Meltwater ponds forming at the edges of volcanic features. Thin places in the ice where the glacier was stretched over a warm water current or a geothermal source, thin enough that light filtered through in blue-green columns. Attenuated and cold but present. These were not comfortable places. The chemistry of meltwater, ponds in a world of acid air and frozen rock, would have been strange by modern standards. But the photosynthesizers that were trying to survive in them had been evolving for 3 billion years by then. They had seen strange chemistry before. And then there is the ice itself. Not all ice is the same. A glacier that is a kilometre thick at its heart is near opaque, yes, but at its edges, at the margins where it thins as it extends towards sea level, where it stretches itself over shallow rock and warm upwelling water, the ice can be thin enough that it is translucent rather than opaque. Not transparent, not like glass, but translucent in the way that a cloud is translucent, letting light through in a diffused and scattered form. Enough light for photosynthesis? In the modern ocean, photosynthesis still proceeds at depths of 100 meters in water that is far less transparent than thin ice. The threshold is low. Not zero, but low. And where the cryogenian ice thinned to tens of meters rather than hundreds, the math may have worked. Just barely, and perhaps intermittently, and perhaps only in the summer months when the sun's angle was better, but perhaps worked. These refugia, the cryoconite holes, the volcanic margins, the thin ice shallows, are the biological argument for the slushball rather than the hard snowball. We know that photosynthetic life survived. We know it because it is there on the other side of the glaciation. Because the algae and the eukaryotes did not disappear from the fossil record permanently. They emerge after the freeze, which means they came through. And if the ocean had been frozen solid to the shoreline everywhere, if every last meter of surface water on the entire planet had been locked under a kilometer of opaque ice, it becomes very difficult to see how they managed it. The refugia are the evidence of their own existence. The photosynthesizer's survival argues backward in time, insisting that somewhere, in some way, light and liquid water coexisted, even if the how and the where remain partly uncertain. But the ocean below the ice, the vast sunless depths that the glaciers pressed over, that is a different story. And it is a story written in iron. Banded iron formations are one of geology's most distinctive rock types. They form in deep water under specific chemical conditions when the ocean contains abundant dissolved iron, iron that has not yet encountered oxygen. Iron that is free to circulate in solution and slowly accumulate over millions of years before eventually settling to the seafloor. Today, the ocean cannot hold iron in this form. Today, the surface ocean is oxygen-rich enough that dissolved iron oxidizes almost immediately and precipitates out. The deep ocean is swept periodically by currents carrying oxygenated water from the surface. And so even the deepest waters are not iron-saturated in the way that would produce thick, extensive iron formations. To make banded iron formations on any significant scale, you need an ocean that is essentially sealed from the atmosphere, an ocean that cannot exchange gases with the air above it, an oxygen-poor, iron-rich ocean that has been cut off from replenishment long enough for the iron chemistry to run. The Cryogenian ocean, under its lid of ice, was exactly this. For the tens of millions of years that the Sturtian glaciation persisted, the ice formed a barrier between the ocean's surface and the atmosphere. The photosynthesis that might have added oxygen to surface waters was suppressed or eliminated in most places. The circulation patterns that mix ocean water that carry oxygen down from the surface to the depths were radically altered or shut down. And the result was an ocean that progressively lost its oxygen and gained iron. Iron dissolved from the seafloor rocks by hydrothermal activity and cold seawater chemistry. Iron that had nowhere to go and no oxygen to oxidize it. Iron that built up in solution, year upon year, century upon century, million upon million year. For more than 1 billion years before the Cryogenian, banded iron formations had been essentially absent from the rock record. The Great Oxidation Event, around 2.4 billion years ago, had transformed the ocean chemistry, had swept the ancient iron-rich seas clean and replaced them with the more oxygenated, iron-poor oceans that persisted through the Proterozoic. The oxygen revolution had changed the chemistry of the world's oceans so completely that the conditions for making banded iron formations simply ceased to exist for over 1 billion years. They reappeared in the Cryogenian. Their reappearance is the ocean telling us, in its chemical language, that it had been sealed, that the oxygen was gone, that the ice had closed the lid. This is one of the ways scientists read the Cryogenian in rock. Not every piece of evidence is as dramatic as glacial debris dropped at tropical latitudes. Not every signal is as visceral as a diamictite, those chaotic boulder and sand mixtures that mark where a glacier shoved and tumbled rock. Some of the evidence is chemical, written in the ratios of isotopes, in the presence or absence of elements, in the mineralogy of seafloor sediments that preserve billions of years later the chemistry of the water that deposited them. The banded iron formations of the Cryogenian are that kind of evidence. They are the ocean's chemical diary, and what they record is a world cut off from the sky. And then there are the carbon isotopes. Carbon comes in several forms, several weights, depending on how many neutrons are packed into its nucleus alongside the protons that define it as carbon. The lighter version, carbon-12, is slightly easier for living organisms to process during photosynthesis. When life is abundant and photosynthesis is running at full speed, the ocean and the atmosphere become slightly enriched in the heavier carbon-13 relative to carbon-12 because the organisms are preferentially pulling the lighter version into their bodies and burying it in sediment when they die. When life collapses, when photosynthesis slows or stops, the ratio shifts. The heavy-to-light ratio falls. Geologists measure this ratio in ancient carbonate rocks and express the result as a value called delta 13c, written with the Greek letter delta followed by a superscript 13 and then c. It is a proxy for biological productivity. A high positive value means life was abundant and active. A deep negative value means it was not. The Cryogenian glaciations are bracketed by some of the most extreme negative carbon isotope excursions in Earth's record. The values fall steeply into deeply negative territory right around the glacial intervals. Think of the delta 13c signal as a kind of productivity meter for the ancient ocean, and what it is showing during the cryogenian freeze is a meter that has dropped close to zero. The biological carbon pump, the process by which living organisms take carbon dioxide out of surface water, build it into their tissues, and eventually carry it to the seafloor as buried organic carbon, had essentially stalled. The ocean was not producing at anything like its normal rate. The photosynthesizers were suppressed. The eukaryotes were hanging on in their refugia, but they were not thriving, not blooming, not running the great carbon cycle at the pace that had characterized the preceding billions of years. The carbon isotopes do not lie. They record what was happening in the ocean at the time the sediment was being deposited, and what they record is an ocean in crisis. Biologically quiet, chemically stressed, running on fumes in the geological sense on whatever scraps of productivity the refugia could maintain. Now hold both things at once. The ocean sealed by ice, iron accumulating, oxygen depleted, the carbon cycle near collapse, and somewhere in the cryoconite holes and the volcanic margins and the thin ice shallows, the last photosynthesizers holding on. These two facts exist simultaneously, and they create a tension that the carbon record and the banded iron formations together preserve for us, compressed into thin layers of ancient rock, waiting for someone to come along with the right instruments and the right questions and read what happened. But there is a question that scientists have not finished answering. A question that sits at the heart of the Snowball Earth story and refuses to be settled, even now, even after decades of study and argument and data collected from every continent where cryogenian rocks are exposed. The question is simple to state and genuinely difficult to resolve. Was the ocean entirely frozen at the surface, every last patch of it? Or was there a band, a persistent zone, perhaps in the tropics, where the ice was thin or absent or intermittent, where open water or near open water survived throughout the freeze? This is the snowball versus slushball debate. And it is not a minor technical disagreement about details. It goes to the heart of what the cryogenian actually was, what it felt like from inside the frozen world, and crucially, how life managed to survive it. The hard snowball position holds that the ice was complete. that when the runaway crossed its tipping point and the world froze, it froze all the way to the equator at sea level, and the ocean surface was covered by ice everywhere, even in the tropics. The proponents of this view point to the tropical glacial evidence, to the Elatina Formation and others like it, to the paleomagnetic data placing glacial deposits at equatorial or near-equatorial latitudes. They point to the climate models, which when run with the conditions of the Cryogenian, the faint young sun, the low CO2 atmosphere, the feedback mechanics, tend to produce complete freezing. They argue that the cap carbonates, those striking layers of tropical warm carbonate sitting directly on top of glacial debris, indicate such an abrupt deglaciation that it is more consistent with a complete freeze than a partial one. A complete freeze that finally broke all at once, they argue, would produce exactly the kind of jarring contact between frozen rock and warm water rock that the caps represent. The Slushball position, sometimes called the Jormungand state, named for the great serpent of Norse mythology that encircles the world and swallows its own tail, suggesting something that wraps all the way around but does not quite close, holds that a band of open or thin ice water persisted in the tropics, that the equatorial ocean was never fully sealed, that the world was nearly a snowball but not quite, a snowball with a thin dark belt of open water running around its middle, different enough from full freezing that it changes the story in important ways. The evidence the Slushball proponents cite includes features within the Cryogenian glacial sequences that suggest the ice was not static, not simply a fixed lid sitting on the ocean for 50 million years without variation. Wave ripples preserved in Cryogenian sediments indicate that open water was present at some point, because waves require open water to form. Advance and retreat cycles within the glacial deposits suggest that the ice expanded and contracted, that it was dynamic rather than frozen in place. These features are read by some researchers as evidence that a working hydrological cycle, with evaporation and precipitation and open ocean circulation, persisted at least in some regions through at least some periods of the glaciations. The snowball proponents have responses. Wave ripples can form under thin ice, in leads and cracks, in marginal conditions that do not require a broad open ocean. The advance retreat cycles may reflect internal glacial dynamics rather than open water periods. The debate goes round and round, each side producing new evidence and new interpretations and new models, and the field has not settled it. Not yet. Probably not for some time yet. What both sides agree on is this: the ice was extraordinary, the extent was extraordinary, the duration was extraordinary. Whatever the precise geometry of the freeze, whether it was hard snowball or slushball, whether a tropical band of open water survived or not, the Cryogenian glaciations were unlike anything that has happened on Earth in the last 600 million years. They were more extreme than any ice age in recorded history, more extreme than the ice ages of the Pleistocene, more extreme by orders of magnitude than anything the modern human species has experienced. The disagreement is about degree, about a band of open water versus complete closure, and both sides acknowledge that even the less extreme option was a world that would be unrecognizable to modern eyes. And both sides have to contend with the same question about life. If the hard snowball is correct, then life survived in the refugia we have described, the cryoconite holes, the volcanic margins, the thin ice shallows. It survived in the margins and the exceptions. If the slushball is correct, then life had more room. A tropical band of open water would have provided a much larger and more reliable habitat for photosynthetic life, a genuinely functional ecosystem running through the worst of the freeze, a biological buffer zone that would make the survival of eukaryotes and algae much easier to explain. The slushball hypothesis is, in some ways, more comfortable biologically. It is easier to understand how photosynthetic life got through a near miss than a complete closure. But comfort is not evidence. The rocks speak their language and the scientists interpret it, and the debate turns on which interpretation fits the full body of evidence better, and that debate is ongoing. What matters for our story, for the long, slow narration of what happened during the Cryogenian, is that in both scenarios the world was under enormous stress, biologically, chemically, physically, and in both scenarios the planet had entered a trap. The trap is elegant in its logic and terrifying in its implications, and it is the thing that makes the Cryogenian not just a cold episode, but a genuine planetary crisis. To understand the trap, you need to think about silicate weathering again, about the process that had helped push the planet into the freeze in the first place. Silicate weathering is the slow dissolution of rock by water and carbon dioxide. Rain falls. It absorbs carbon dioxide from the air as it falls, becoming slightly acidic, becoming carbonic acid, weak and mild, but enough. It hits rock, granite, basalt, the silicate minerals that make up the bulk of the continental crust. The acid in the water reacts with the minerals in the rock. Calcium and magnesium and silicon are released and carried away in solution, eventually to the ocean. And the carbon dioxide that started the reaction is consumed in the process, incorporated into dissolved bicarbonate, carried away, eventually deposited on the seafloor as carbonate sediment. The carbon is removed from the atmosphere. The greenhouse effect is weakened. The planet cools. This process is one of the primary long-term regulators of Earth's climate. It is the planet's thermostat, the negative feedback mechanism that over millions and tens of millions of years tends to bring CO2 levels back toward a workable range whenever they drift too far in either direction. If the planet warms, the evaporation increases, the rainfall increases, the weathering speeds up, more CO2 is drawn down, and the warming moderates. If the planet cools, the weathering slows, volcanic CO2 accumulates, and the cooling moderates. It is a slow, gentle planetary self-regulation, running over geological timescales, keeping the world within the broad range of conditions that life requires. But the thermostat has an off switch, and the Cryogenian threw it. When the ice advanced far enough, when it covered the continents at tropical latitudes, when it blanketed the warm, wet rock that had been running the silicate weathering reaction at such a high rate, the process nearly stopped. Not entirely. There is evidence of some weathering persisting in the cryoconite holes and in the margins and wherever liquid water managed to touch exposed rock. But the great tropical weathering engine, the process that had helped draw down CO2 and help tip the planet into the freeze in the first place, was now buried under glaciers, covered, shut down, and the volcanoes kept erupting. The volcanoes have always kept erupting. That is not a feature of the Cryogenian specifically. It is a feature of having a planet with a hot interior and a thin outer shell and a long history of geological activity. The magma rises, the volcanoes erupt, the gases are released into the atmosphere. Carbon dioxide among them. Always carbon dioxide among them, because carbon is abundant in the mantle, and when hot rock melts and the dissolved gases escape, carbon dioxide escapes with them. The volcanoes do not care about ice ages. They do not slow down because the surface is frozen. They continue to emit carbon dioxide at roughly the same rate they always have because the geological processes that drive them. The slow convection of the mantle, the plate movements, the heat from radioactive decay in the planet's interior, none of these processes know or care what is happening at the surface. So, the thermostat is off. The weathering has stopped, or nearly stopped. The volcanoes are still running. CO2 is being added to the atmosphere, and nothing is removing it. Year after year, century after century, millennium after millennium, the gas accumulates. In the normal operation of Earth's climate system, this would not be a crisis. The thermostat would catch it. A little extra CO2, a little warming, a little more evaporation, a little more rainfall, a little faster weathering, a little more drawdown. Balance restored. But the ice has broken the thermostat by covering the rock. There is no weathering to speed up. The ice is too reflective to allow the sun to warm the surface enough to melt it. The feedback that could restore balance is buried under the very ice that caused the problem. The planet is locked. This is the trap. A planet that cooled itself into a frozen state and cannot cool itself further, but also cannot warm itself out. Because the warming mechanism, the CO2 accumulation signal that would normally trigger the thermostat response, has no response available. The CO2 is accumulating slowly and patiently because there is nothing to stop it. But the ice is too thick and too reflective for the weak additional greenhouse effect to overcome it yet. Not yet. The balance of forcing is still on the side of cold. The ice wins. For now. For 10 million years. For 20 million. For the full terrible span of the Sturtian. Try to feel the scale of that. 57 million years. The CO2 climbing. The ice holding. The volcanoes emitting into a sealed sky, the iron accumulating in a sealed ocean, the photosynthesizers clinging to the margins, the carbon isotopes recording a near-silent biological world. 57 million years is longer than the entire span from the extinction of the non-avian dinosaurs to this moment. It is longer than the entire Cenozoic era, the age of mammals, the age that contains every primate, every hominid, every human being and ancestor of human beings that has ever lived. The Sturtian glaciation lasted longer than all of that combined by a significant margin. And during all of that time, the CO2 climbed. The rate of volcanic emission was not dramatic. Volcanoes add CO2 to the atmosphere slowly by human standards, slowly even by historical standards. A volcanic eruption, even a large one, adds a relatively modest amount compared to the total atmospheric reservoir. But the planet has a lot of volcanoes. And over millions of years, the small, steady additions mount up. The concentration that began the Sturtian at some already depressed value, already drawn down by the great weathering machine of tropical Rodinia, began to climb. Slowly, a few parts per million per thousand years perhaps, nothing dramatic in any given century. But the centuries accumulated, and the CO2 accumulated with them. The models suggest that by the time the ice finally broke, and we will come to how it broke, to the mechanics of the thaw, to what finally happened when the accumulated pressure of all those millions of years of volcanic emission finally overcame the ice's hold on the world, the CO2 concentration may have reached something in the range of 1/10 of a bar. 1/10 of an atmosphere composed entirely of carbon dioxide. That is the number the models suggest, the order of magnitude that the geological evidence is consistent with. 1/10 of a bar. Compare that to pre-industrial CO2 concentrations of roughly 280 parts per million, which is to say roughly 280 millionths of a bar. The cryogenian CO2, at the height of its accumulation, may have been running at something like 350 times that pre-industrial value. 350 times. The sky over the frozen world was heavy with a gas that the world had no way to remove. The trap had been running for tens of millions of years. The thermostat was buried under ice. The volcanoes were still erupting, and the CO2 was still climbing, patiently, invisibly, adding to a pressure that was building towards something the frozen surface of the planet could not hold forever. But that release had not come yet. Not at the point where we are in this story. The ice was still holding. The world was still in winter. The ocean beneath the ice was still iron-rich and oxygen-poor and biologically suppressed. The photosynthesizers were still clinging to their refugia, to the cryoconite holes and the volcanic margins and the thin translucent shallows, doing the slow work of staying alive in a world that had nearly stopped being habitable for them. The carbon isotope record was still showing deep negative excursions. The productivity of the ocean was still near collapse. The banded iron formations were still being deposited in the dark sealed deeps. The diamictites were still being laid down at tropical latitudes. The dropstones, those individual boulders released by floating ice and plunging into the fine-grained seafloor sediment and bending the layers beneath them like a stone dropped into wet clay, were still recording in stone the presence of ice at sea level in places that should, by all rights, have been warm. And above it all, the question that the Slushball debate keeps open. Was there a dark belt of ocean running around the equator, thin ice or open water, a biological corridor, a zone of survival wider than a cryoconite hole? Or was the closure complete? The ice solid from pole to tropical shore, the ocean lid unbroken. The evidence goes on being ambiguous. The wave ripples in the cryogenian sediments go on being wave ripples, suggesting open water to some researchers and a more complicated picture to others. The advance retreat cycles in the glacial sequences go on being interpreted in different ways, by different scientists, with different models and different assumptions. The hard snowball modelers and the slushball proponents go on publishing papers and attending conferences and presenting their cases, each citing real data, each with real arguments. Each convinced the evidence supports their reading. What neither side disputes is what was building in the sky. The CO2, invisible and odorless, accumulating above the frozen surface of a planet that had sealed its own thermostat under ice. Accumulating, year by year, volcano by volcano, eruption by eruption, in the cold and silent air over a world that was waiting. In the way that only geology can wait for the balance to shift. It would shift. It always shifts. The geological record is, among other things, a record of how planetary systems find their way out of traps, of how the slow accumulation of pressures eventually overcomes even the most stable-seeming states. The ice had held for tens of millions of years, and it felt absolute from inside the freeze. But it was not absolute. Nothing on a planet with a hot interior and a long future is absolute. The CO2 was climbing, the trap was set. The accumulation was patient and vast and utterly relentless, the way that geological forces are relentless, the way that a dripping tap fills a bathtub, the way that a millimeter of sediment per year becomes a kilometer of rock in a million years. Slow, unspectacular in any given moment, and inexorable. And the frozen world did not know it was already carrying the key to its own release, did not know that the very mechanism that had helped freeze it, The volcanic activity that had kept emitting CO2 even through the catastrophe was slowly, patiently, over unimaginable spans of time, loading the atmosphere with the precise thing that would one day break the ice. That would shatter the reflective surface of the world. That would end the longest winter in the planet's history in a catastrophe of heat that would make the freeze look, in retrospect, almost gentle. The CO2 was climbing, the ice was holding, the refugia was small and scattered and barely enough, and the planet held its breath. And so the counting began. Not in years, because years are too small a unit for what was happening. Not in thousands of years either, or even in hundreds of thousands. The counting happened in millions of years, the way that only the deepest geological processes count, the way that the ocean fills sediment, trays a grain at a time, and calls it progress. The CO2 was climbing in millions of years, increments. Volcanic vents were leaking it into the air from beneath the ice sheets, from beneath the frozen ocean, from the places where the crust was thin and the mantle close. Each year, a little more. Each 10,000 years, a measurable rise. Each million years, a step that models can resolve and that changes the arithmetic of the atmosphere by a detectable degree. Picture the atmosphere of a frozen Earth as a very slow bank account. Normally, on a living planet with liquid oceans and wet continental shelves and running rivers crossing exposed rock, that account is kept roughly balanced. CO2 goes in from volcanoes. CO2 comes out through silicate weathering, rock dissolving slowly in rainwater, carbonate ions washing into the sea. The deposit and the withdrawal more or less match over geological time. The balance stays within the range that keeps the planet temperate, that keeps the water liquid, that keeps the cycle turning. The whole system is a kind of slow thermostat, and it has kept Earth livable for billions of years, the reason, among reasons, that Earth has liquid oceans at all when Venus, its near twin, boiled dry and Mars froze solid. But the snowball broke the thermostat. When the ice clamped down and covered the continents and sealed the ocean, the withdrawal side of the ledger vanished almost entirely. There was no liquid rainwater on exposed rock. There was no river dissolving silicate minerals and carrying bicarbonate to the sea. The chemical weathering that normally sponged CO2 out of the air simply stopped, not slowed. Stopped, the ice was too cold, too thick, too complete to allow the liquid water chemistry that weathering requires. And the deposits kept coming. The volcanoes did not stop. Volcanoes are indifferent to surface conditions. They erupt from the planet's interior, driven by pressures that have nothing to do with whether the surface is frozen or warm or carpeted in forest. Hotspots kept bubbling. Mid-ocean ridges kept spreading. Subduction zones kept pushing rock into the mantle and returning gases to the surface. CO2 kept rising from the ground and entering the air. With no way out, it accumulated. The way that debt accumulates when you stop paying and interest keeps running. The way that water builds behind a dam whose outlet is blocked. Slowly, steadily, over millions of years, the concentration of carbon dioxide in the atmosphere of the frozen Earth climbed to levels that have no modern analogue. Models suggest that by the time the Sturtian glaciation finally ended, the atmosphere held something on the order of 1/10 of one atmosphere of CO2 pressure. Write that as a fraction, 0.1 bar. Now compare it to the pre-industrial concentration that held for most of human civilization, roughly 280 parts per million, which is 280 millionths of the atmosphere, or about 0.0028 bar. The frozen world's CO2 load was approximately 350 times that. 350 times. Not a percentage increase. A multiplication by 3.5 centuries worth of concentration packed into a single atmospheric column above a frozen world. That is the number that broke the ice. Think about what it took to get there. The Sturtian alone lasted 57 million years. 57 million years of volcanoes leaking CO2 into air that had no exit. 57 million years of the atmospheric account accumulating with nothing spent. There is no human experience that maps to 57 million years of patient accumulation. The entire span from the first dinosaurs to today is roughly 250 million years. The Sturtian freeze was nearly a quarter of that. A single unbroken cold season lasting a span of time within which continents moved, species evolved and vanished, mountain ranges rose and were worn flat, and through all of it the CO2 was rising, patiently, indifferently, inexorably toward the threshold. The threshold is not a mysterious thing, it is simple physics, the same physics that makes greenhouse warming work on any rocky planet with an atmosphere. Carbon dioxide absorbs infrared radiation, it traps heat that would otherwise escape to space. Add enough of it and the energy balance of the planet shifts, more heat absorbed than lost, and the temperature rises. On a temperate world with a stable climate, this effect is balanced by the silicate weathering that draws CO2 back down. But on a world already locked in ice, the only thing that matters is whether the warming effect of accumulating CO2 can eventually outmatch the cooling effect of a planet-wide mirror. The ice was reflecting sunlight with extraordinary efficiency. A frozen world with ice from pole to equator sends roughly 60 to 70% of incoming solar energy straight back to space. That is the reflective armor that made the freeze so stable for so long. The sun was trying to warm the planet, and the planet was bouncing most of it away. But the CO2 was adding warmth from the other direction. Not from incoming sunlight, but from trapped outgoing heat. Every molecule of CO2 added to the atmosphere slowed the escape of infrared radiation, like adding another blanket above the frozen surface. And CO2 molecules, unlike sunlight, do not care whether the surface below is white or dark. They trap heat regardless. So while the ice kept deflecting the sun, the thickening blanket of CO2 above the ice was slowly tightening. Eventually, and in geological time eventually arrives, the balance tipped. The warming from the greenhouse blanket began to win against the cooling from the reflective surface. At some latitude, at some moment in deep time, a patch of ice grew thin enough to show a sliver of darker ground or darker water beneath it. Darker surfaces absorb more sunlight. The absorbed energy warmed the area slightly, melted a little more ice, exposed a little more dark surface. The ice albedo feedback that had frozen the planet in the first place now ran in reverse. The reflective armor began to crack, and once it cracked, the reversal was as violent as the freezing had been. The models suggest the deglaciation was, by geological standards, rapid, centuries, perhaps a few thousand years. An eye blink, given the tens of millions of years of cold that preceded it. The ice that had accumulated over incomprehensible spans of time melted in a geological instant. The oceans, which had been sealed beneath their frozen lid, were exposed to an atmosphere carrying 350 times the pre-industrial CO2 load. The world did not warm gently back to temperate. It overshot. Badly, estimates of global mean surface temperature during the post-Snowball supergreenhouse run as high as 50 degrees Celsius, average, not a tropical high. average, the equatorial regions, already the warmest zones on any planet, would have been staggering, barely habitable by any standard we recognize. The ice sheets, collapsing, released meltwater into seas that were already rising fast. Sea levels climbed as the glaciers gave back their water. The hydrological cycle, which had been suppressed for tens of millions of years, roared back with extraordinary violence. Rainfall was not gentle. The atmosphere was hot, humid and saturated with CO2 at concentrations that made the precipitation chemically acidic, carbonic acid falling from a burning sky, dissolving fresh rock with ferocious efficiency, the silicate weathering machine restarting at maximum speed. The cap carbonates record all of this. They are the rock layer that makes the Snowball Earth story legible in stone, the geological fingerprint of a deglaciation more violent than anything the modern world has experienced. Directly on top of the glacial diamictites, the chaotic, poorly sorted rubble dumped by glaciers, the fingerprint of ice, lies a layer of carbonate rock. Dolostone, limestone, tens of meters thick in many sections, formed in water that was warm and alkaline and saturated with dissolved carbonate ions. The juxtaposition is stark enough that any geologist who encounters it for the first time stops. Cold water glacial debris, then warm water carbonate. Freeze, then furnace. The cap carbonates are not a gradual transition. They sit on the glacial rock like a signature, like punctuation at the end of an ice age that lasted tens of millions of years. The chemistry that formed them was the chemistry of an ocean trying to absorb an atmosphere dense with CO2. The dissolved gas reacted with the alkaline meltwater of the thawing ice and precipitated out as carbonate minerals, covering the seafloor in what must have been an extraordinary chemical deluge. In the Flinders ranges of South Australia, you can stand at the outcrop and put your hand on the boundary. Below your fingers, cold. Above your fingers, warm. The whole story of the Sturtian, or the Marinoan, depending on which layer you are reading, compressed into a few centimeters of rock. The two worlds, touching. This is what the Cryogenian did. Not once, but twice. Because here is a thing that often gets lost in the broad telling. The snowball was not a single event. It was two. The Sturtian glaciation, the longer one, the one that lasted 57 million years, ended around 660 million years ago. And then, the planet recovered, warmed back towards something habitable. The super greenhouse released its grip over millions of years as the silicate weathering machine pulled CO2 back down to manageable levels. The ice retreated, liquid water returned to the surface. Something like normal conditions prevailed for roughly 10 million years. That interval is recorded in sedimentary formations, among them the Rostov and Trezona formations that show open water, non-glacial deposition, warm sediment. The chemistry of a living ocean, life surviving and perhaps tentatively diversifying in the aftermath of the first great freeze. A reprieve, a parenthesis in the cold, a breathing space of 10 million years between the most extreme climate events Earth had yet experienced. And then, around 650 million years ago, the whole cycle started again. The Marinoan glaciation. A second snowball, or second near snowball. The debate about whether the Marinoan was as complete as the Sturtian, whether it truly achieved hard snowball conditions, pole to pole, is still alive. But the evidence for its global reach is strong. Low-latitude glacial deposits, cap carbonates at its termination. The same signature, the same fingerprint, recorded on continents scattered across the ancient ocean. A second time, the world reached the tipping point and fell into the freeze. Why? The same set of forces that drove the Sturtian was still in play. The continents were still in the tropics. Silicate weathering was still capable of stripping CO2 faster than volcanoes could replace it, given the right conditions. The faint young sun was still dimmer than it is today. The window for runaway glaciation was still open. It only needed the right push, and the right push, in deep time, always eventually arrives. The Marinoan lasted perhaps 15 million years, shorter than the Sturtian, which was already the longest individual ice age in Earth's known history. It ended sharply around 635 million years ago. Sharply, in geological terms, the cap carbonates of the Marinoan termination are striking for the abruptness of the transition, the same volcanic CO2 escape mechanism triggering another runaway thaw, another super greenhouse, another acid rain episode, another deposition of carbonates on the floor of a warming ocean. The planetary thermostat overpowered twice in succession, breaking in the same direction both times. After the Marinoan, no third snowball, or at least nothing of the same scale. The Glaciers glaciation, which followed around 580 million years ago, is worth naming because it is often mentioned in the same breath as the Cryogenian events. But the contrast is instructive. The Glaciers was regional, not global. It lasted perhaps 1 million years, a fraction of even the shorter Marinoan. It left glacial deposits, but not the low-latitude, planet-wide signature of the Cryogenian freezes. It was a glaciation in the ordinary sense, severe by modern standards, perhaps comparable to the ice ages of the past 2 million years that put ice sheets over Chicago and London, but categorically different from what the Sturtian and Marinoan had done to the planet. The Glaciers is a useful measuring stick. It tells you what a normal, non-snowball glaciation looks like in the rock record, so that when you look at the Cryogenian deposits and see low-latitude diamictites and planet-wide cap carbonates, you understand why the scientists who study them talk about them in such different terms. The Glaciers is dramatic. The Sturtian and Marinoan were something else entirely. Something the planet has, as far as we know, done only once in the Neoproterozoic era at that scale, though not for the first time in its long history. Because the Cryogenian was not the first snowball. The deep record holds an earlier episode, much older, from around 2.4 to 2.2 billion years ago, the Huronian glaciation, also called the Makganyeni glaciation in some of its phases, which may itself have achieved global or near-global extents. It followed closely on the heels of the Great Oxidation event, the moment when photosynthetic bacteria first flooded the atmosphere with oxygen in significant quantities. The oxygen destroyed much of the methane that had been warming the early Earth, and the temperature crashed. The earliest snowball, or near snowball, triggered by life's first great chemical revolution. The Cryogenian, then, was the second act. The encore. A planet that had been through this before, that had found its way out of the trap before, that was carrying the memory of a previous freeze written in the rock below the Sturtian strata. Not that the planet knows anything, of course. The planet does not remember. But the record does. And reading the record, you see the same mechanisms playing out twice, separated by nearly 2 billion years of non-snowball history, with the same kinds of escape valves, the same volcanic patience, the same atmospheric chemistry, ultimately restoring equilibrium. Life made it through both. Which brings us to what may be the most remarkable part of the whole story. Not the freezing, not the thawing, Not the staggering duration, not the cap carbonates, not the banded iron formations. The most remarkable part of the Cryogenian is what came after it. When the Marinoan glaciation ended, sharply, around 635 million years ago, something changed in the ocean that was not merely a return to pre-freeze conditions. The ocean was different. The world was different. The glaciers had done something to the continents over the course of their long tenure. All that grinding, all that crushing weight of ice moving across exposed rock had pulverized the continental surfaces in a way that liquid water and wind alone cannot match. Glaciers are geological mills. They take rock and reduce it to powder, glacial flour. The pale fine sediment that gives glacial rivers their milky grey-green colour. And that flour, that pulverized rock, carries something that running water dissolves and carries to the sea. Phosphorus. Phosphorus is one of the essential nutrients for life. It is the backbone of DNA, a component of cell membranes, a key player in the energy metabolism that powers every living cell. In the modern ocean, phosphorus is a limiting nutrient, meaning that the amount of phosphorus available often determines how much life can grow, the way that the size of a container determines how much water you can pour into it. More phosphorus means more algae. More algae means more organisms feeding on algae. More of those means more organisms feeding on them. All the way up whatever food chain the ecosystem supports. When the Marinoan ice sheets melted, they released an enormous pulse of glacially ground continental rock into the oceans. The weathering machine, restarting at full speed in the acid rain heat of the post-snowball super greenhouse, flushed phosphorus and other nutrients into the sea at rates that had not been seen in millions of years. The ocean, which had been a nearly sealed, depleted, banded iron-poisoned body of water for much of the Cryogenian, was suddenly, geologically speaking, drenched in the nutrients that life needs to bloom. And life bloomed. Jochen Brox and colleagues documented this story in work published in 2017. They analysed molecular fossils, steranes, the chemical remains of cell membranes preserved in ancient rock, and found a sharp rise in the steranes characteristic of eukaryotic algae right after the Cryogenian glaciations. Before the freezes, the ocean had been dominated by simpler, smaller microbial life. After the freezes, the algae rose. Complex, nucleus-bearing cells with sophisticated internal machinery. The kind of cells that would eventually build into the multicellular bodies of animals, surged in abundance and diversity. The rise of the algae, that is the phrase, and it means more than a simple biological shift. Algae are photosynthesizers, meaning they pull CO2 out of the water and release oxygen. More algae means more oxygen being produced. More oxygen released into an ocean that had been, during the snowball, almost entirely anoxic, starved of oxygen by its ice lid and its disconnection from the atmosphere. The oxygen began to build. Not immediately to the levels we breathe today, but the trend toward oxygenation that complex animal life requires was being driven forward, partly by the algal bloom that followed the glaciations. The nutrient flush fueled the algae. The algae drove oxygenation. The oxygen opened a door. What came through that door, eventually, was the Ediacaran. The Ediacaran period follows the Cryogenian in the geological record. It runs from around 635 million years ago to roughly 539 million years ago. And it contains something the Cryogenian does not: the first large, complex, multicellular organisms whose fossils can actually be seen. Not chemical traces, not molecular ghosts, but shapes. bodies, things that had enough structure and enough size to leave impressions in soft seafloor sediment that survived for hundreds of millions of years. Dickinsonia, a flat, oval, quilted thing, growing up to 1.5 meters long, which lived on the seafloor in the Ediacaran seas. Its exact nature is still debated, but the evidence points to it being one of the earliest animals, or at minimum a complex multicellular organism in the lineage that led to animals. Its body plan is unlike anything alive today, a design the planet tried and ultimately set aside. But it was real, and it was there, and it left its shape pressed into sandstone in the Flinders Ranges of South Australia. The same Flinders Ranges that hold the glacial record of the Sturtian and Marinoan. Charnia, another Ediacaran organism, frond-shaped, anchored to the seafloor like a plant, but almost certainly not a plant. Found in England, in Newfoundland, in Russia. Complex enough to have had differentiated parts, to have grown in a structured way, to have left a distinct impression that paleontologists recognized immediately as something other than the simple microbial mats and colonies that had dominated the Precambrian Ocean for billions of years before. These organisms were not there before the Cryogenian glaciations. The freeze came, the world held its breath for tens of millions of years, the ice broke in a runaway thaw, the nutrients poured in, the algae rose, the oxygen climbed, and then, in the Ediacaran, the first complex multicellular bodies appeared in the fossil record. The timing is striking enough that many researchers take it seriously as a causal chain, not just a coincidence of dates. The freeze may have done something to the ecological and evolutionary landscape that made the emergence of complex life easier, or faster, or more likely than it would have been otherwise. Perhaps the near extinction of so much microbial life cleared competitive space for new designs. Perhaps the nutrient flush was the enabling condition that had been missing before. Perhaps the oxygenation pushed by the algal bloom reached the threshold that energy-hungry animal cells require. Perhaps all of these things, acting together over the 30 million years between the Marinoan termination and the appearance of Dickinsonia in the fossil record. It would be too simple to say the snowball caused complex life. The chain between two events separated by tens of millions of years is never a clean, single-link chain. But it would also be too dismissive to call the connection accidental. The Cryogenian was not a background episode in a story mainly about something else. It was a restructuring event. The planet that emerged from the Marinoan was geochemically, biologically, and ecologically different from the planet that had entered the Sturtian. The ocean had been purged and refertilized. The atmosphere was on a different trajectory. The survivors of the freeze, the organisms that had clung to thin ice and volcanic warmth and cryoconite holes and pockets of translucent slow light, had been filtered and tested and perhaps simplified in ways that made subsequent diversification easier to trigger. The freeze was not the death of the story. It was the opening of the next chapter. Or perhaps, and this framing may be the truest of all, it was a form of planetary editing. A long, brutal, patient rewrite that stripped away the version of the biosphere that had dominated for over 1 billion years and left the page cleaner for what came next. Whether that is a story of self-repair is a question of perspective. The planet was not trying to repair itself. There was no intention, no direction, no goal. The physics and chemistry were blind and indifferent, operating on their own terms. But the outcome, read from the vantage point of the present, reads like repair. A world that had gone to its coldest extreme, held there for geological ages, and returned from it not just intact, but fundamentally changed in a direction that led, eventually, to complexity, to Dickinsonia and Charnia, to the explosion of animal life in the Cambrian that followed the Ediacaran, to eyes and nervous systems and motion and predation and all the Baroque elaborations that evolution builds when oxygen is available and ecological space is open and the raw materials are there. To, eventually, everything that followed, including the particular lineage of complex, oxygen-breathing, large-bodied organisms that would one day stand in the Flinders ranges of South Australia and find Dickinsonia pressed into a cliff face, and feel the weight of the question about how it got there, and begin to piece together a story that stretched back 600 million years to an ocean sealed beneath a kilometre of ice, including, if you want to take the chain to its full and slightly vertiginous extent, you. And here the slushball question reasserts itself, quietly, as it has throughout this story. Because we don't entirely know that the surface froze solid everywhere. The debate between the hard snowball and the Jormungand state, the possibility of a band of open or thin ice tropical water persisting through the Cryogenian, has not been settled. There is evidence that presses in both directions. The wave ripples within some glacial sequences, the advance-retreat cycles in certain sediment layers are read by the slushball proponents as signs of a working hydrological cycle, of open water and seasonal dynamics, not a solid planetary lid. The hard snowball advocates counter that these features can form beneath thin ice, that the low-latitude glacial records and the banded iron formations and the scale of the CO2 buildup all point to a world that was, at minimum, extremely close to completely frozen. Both camps are arguing from real rocks, real chemistry, real physics. Neither is simply wrong. The question is one of degree, not whether the Cryogenian glaciations were extreme and global, because they clearly were, but whether the very last patches of open tropical water survived, and what that would mean for the life that had to endure the freeze. If a band of equatorial ocean remained ice-free or ice-thin, then refugia were larger than the tight, precarious spaces we imagine for a hard snowball. If the ocean froze solid to the equator, then life's survival through 57 million years of Sturtian cold becomes even more improbable and even more astonishing. The scientists are still working on this. The Flinders Ranges still have rock sections to study. New isotope systems are being developed that may resolve what older techniques cannot. Computational models are being refined, run at higher resolution, tested against better data. The question is alive and will likely remain alive for some time, perhaps for a generation of researchers who are still in school right now, who will one day stand at an outcrop in South Australia or Namibia or Oman and look at a piece of cryogenian sediment with new tools and perhaps, finally, tip the balance one way or the other. Or perhaps not. Some questions in deep time settle slowly, some settle with a whisper rather than a declaration. And there is something fitting about this particular uncertainty persisting at the heart of the Snowball Earth story, because uncertainty is what the deep past genuinely is. We are reading, from stone and chemistry and magnetism, a story that was not written to be read. The rock does not intend to communicate. We are finding signal in the noise of geological time, constructing a narrative from discontinuous data separated by hundreds of millions of years of burial and metamorphism and erosion. And then we are being honest, the best of us are being honest, about where the signal runs out and interpretation begins. That honesty is not a weakness in the science. It is the science. The willingness to hold the hard snowball and the Jormungand state simultaneously, to argue from evidence without papering over the gaps, to leave the question open when the evidence genuinely does not close it, that is how knowledge of deep time actually works. And that open question, the sliver of maybe open water, the possibility that the tropics held something liquid through the worst of it, is part of what makes the cryogenian story feel alive rather than settled and archived. We know the ice was there. We know it reached the equator. We know it held for tens of millions of years. Twice, we know the CO2 built up and broke it. We know the thaw was violent and hot and chemically extreme. We know the cap carbonates formed and the nutrients flushed, and the algae rose and the Ediacaran life followed. And we do not fully know, not with the certainty that some questions in geology have been resolved, whether the last patch of sunlit water somewhere between the tropics survived through the depths of the Sturtian cold, or whether the world was truly, completely, horizon to horizon, pole to equator, a white and silent sphere drifting through the ancient dark. That single unknowing is the story's last gift, the invitation to sit with something unresolved, to let the mystery remain where the evidence cannot yet reach. And tonight, lying still, letting these thoughts settle through you the way that sediment settles through still water, slowly, by gravity, without effort. You are at a very comfortable distance from all of it. 650 million years is not a distance that produces anxiety. It is a distance that produces something quieter, something that feels, if you let it, like perspective. The kind of perspective that comes from holding a very long timeline against a very short life and finding, in the comparison, not smallness, but a strange sort of ease. The Sturtian lasted 57 million years. Your worries last what? Days, sometimes weeks, at most. The scale is so different that they barely share a unit of measurement. And the planet that held a Sturtian winter for 57 million years is the same planet you are lying on right now. On the other side of 650 million years of subsequent history, with its oxygen atmosphere that the algae helped build, its complex ocean ecosystems that the Ediacaran biota made possible, its air that Dickinsonia and Charnia and all the nameless soft bodies of the Ediacaran prepared the way for. You are breathing the legacy of a thaw that happened before there were eyes to see it. The CO2 that climbed to 350 times its normal level beneath a planetary lid of ice has long since been drawn back down through eons of silicate weathering and carbonate burial and photosynthetic oxygen production and all the other slow chemical cycles that the living Earth runs continuously, like a body running its metabolism, like a breath taken and released over millions of years. The super greenhouse that followed the Marinoan termination and pushed surface temperatures to 50 degrees on average raged for thousands of years and then faded, drawn down by the same patient chemistry that has always moderated the extremes, always found the middle, always restored something like equilibrium over geological time. The cap carbonates sit quiet in the Flinders ranges. The banded iron formations sit quiet in the deepest sedimentary layers below the caps. The diamictites, the tillites, the chaotic glacial rubble dropped by ice that no longer exists, are quiet in their strata, patient as only stone can be patient, holding the record of the coldest the planet has been in the last 500 million years in a form that a person with a hand lens and a compass can read, given time and training and the willingness to kneel in the sun on an Australian. hillside and look closely at the contact between one world and another. The dropstones are there too, individual pebbles plucked by floating ice from a distant shore, carried out over an open or ice-covered sea, released as the ice melted or cracked, falling slowly through the water column and landing in the soft mud of the seafloor with enough force to bend the fine sediment layers beneath them like a dimple pressed into a mattress. Those bent layers have been preserved for 650 million years. They are in the rock right now, in outcrops that anyone can visit, in sections that geologists have measured and mapped and photographed and argued over, evidence so tangible and so unambiguous that it was among the first lines of evidence that Brian Harland assembled in the 1960s when he first argued that the Precambrian glaciations had been near global in extent. Harland saw the dropstones. He saw the low-latitude glacial rocks. He did not yet have the paleomagnetic data that would confirm their equatorial positions, and he did not have the ice albedo feedback calculations that Boudico and Sellers would publish in 1969, and he did not have a name for the hypothesis he was building. But he had the rock, and he trusted the rock, and he followed the evidence to a conclusion that most of his contemporaries found implausible. It took Joseph Kirschvink in 1992 to give the idea its name and its mechanism. It took Paul Hoffman and Daniel Schrag in 1998 to build it into a full integrated model that the geological community could test and argue about and build upon. And it has taken the decades since then to fill in the details, the UPB zircon dates that pin the Sturtian onset at precisely 717 million years ago, the molecular fossil evidence from Jochen Brock's that traces the rise of algae in the aftermath, the computational models that estimate the CO2 threshold for escape, the ongoing fieldwork in South Australia and Namibia and Oman and Svalbard that continues to add data points to the Snowball versus Slushball debate. Science is slow too, not as slow as the Sturtian, but slow in its own way, following evidence instead of conclusion, accumulating certainty the way that CO2 accumulated beneath a frozen lid, one paper at a time, one field season at a time, one revised model at a time. The story of Snowball Earth is not finished. The scientists working on it are still working on it. The rock still has things to say. But what the record has already told us is enough for tonight. Enough for the particular kind of wondering that comes late, in quiet, when the world is still and the mind is soft, and the distance between now and 650 million years ago feels not like a barrier, but like a depth to sink into. A world that froze. Completely, or almost completely, the debate lives on. A world that held its cold through 57 million years of Sturtian night, and then recovered, briefly, and then froze again through the Marinoan. A world that sealed its own ocean and poisoned it with iron and collapsed its own carbon cycle and accumulated, beneath the ice, the very gas that would eventually free it. A world that thawed in a catastrophe of heat and acid rain and cap carbonates and rising seas, and then, against what seems, from the outside like terrible odds, bloomed, algae rising, oxygen climbing, Ediacaran bodies taking shape in the softened sediment of a warming sea. A world that, in its slow, indifferent planet-scale way, found its way from the deepest cold to the richest complexity. Not because it was trying to, not because it was directed toward any outcome, but because physics and chemistry and time are sufficient, given enough of all three, to produce outcomes that look, from the inside of one of those outcomes, like miracles. The ice that swallowed the entire planet could not hold everything. Something always survived, something always small and inconvenient, and tucked into the last warm corners, the cryoconite holes with their thin, dark water, the volcanic vents with their mineral-rich heat, the translucent patches of ice where photons still reached and chlorophyll still turned sunlight into sugar. Barely, just enough. Life is not fragile in the way we sometimes feel it is. It is tenacious in ways that the Cryogenian tested to an extreme that has not been repeated since. And it held on. It held on. And the CO2 climbed, and the ice broke, and the algae rose, and the Ediacaran came. And eventually, much later, so much later that the Cryogenian was buried under 600 million years of subsequent rock, something on the surface looked at the sky and wondered. That wondering is tonight. You are it. Let the deep thoughts settle and let yourself sink with them.